Hi, I'm Swarupa Sail, course instructor for Geotechnical Engineering 1. In this presentation, we will go through interpretation of consolidation test results and how to derive coefficient of volume compressibility. In theory of compression, soil compression is assumed to occur by the decrease in the volume of voids. So when the soil is loaded, it is going to compress, and that compression is due to removal of either air or water from the voids. So since there is removal of air or water from the voids, there is decrease in the volume of voids. Whereas the volume of solids is assumed to remain constant throughout the process. Once the total load due to structure on the soil increases, there is increase in the total stress. In order to resist this total stress, effective stress, which is the stress exerted by soil particles, also increases. Hence, there will be higher compression. So, the compressibility of soil is expressed in terms of a plot which is drawn between void ratio E on y-axis and effective stress sigma dash on x-axis. Voids ratio is the ratio of volume of voids to the volume of solids, and it is used to represent compression. The volume of voids is the reflective of compression, and volume of solids is assumed to remain constant. We know that the construction of a structure takes place in stages. That means the structure is not constructed at once. So each component of it is constructed stage-wise. So due to which there will be increase in the stress on soil also in increments. And this condition of field can be represented in laboratory using consolidation test. And while conducting this test, the stress is applied in increments, because on site also the construction of structure results in increase of stress on soil in increments. And this test is conducted on undisturbed soil specimen, and this soil specimen will be allowed to consolidate for sufficient time under each stress increment. A typical laboratory consolidation test consists of loading an undisturbed soil specimen with the given stress increment, and the vertical compression of the soil specimen is noted down with a dial gauge at regular time intervals for sufficient amount of time. The next stress increment is applied only after the compression of the soil is completed under the previous stress increment, and the process is repeated. So for each application of stress, the soil is allowed to compress for sufficient amount of time, and after that the next stress is applied. There are two types of results that are obtained from laboratory consolidation test. The compression of a soil as a function of effective stress increment is expressed as a relation between the final void ratio E, which is also known as equilibrium void ratio on the y-axis, versus effective stress sigma dash on the x-axis. And this can even be represented by E versus log of sigma dash curve. Here we can see a graph which is drawn for void ratio on y-axis and effective stress sigma dash on x-axis. So this is the curve which is obtained by consolidation test. Sigma 1 dash is the applied effective stress and E1 is the corresponding void ratio. Similarly, sigma 2 dash is the next stress increment and corresponding to which is E2 as the void ratio. The difference between E1 and E2 is nothing but change in void ratio, which is represented by delta E. And the difference in effective stress, that is sigma 2 dash minus sigma 1 dash, is delta sigma dash, which is the change in the effective stress. And when we draw a graph of void ratio versus log of effective stress, we get a straight line. And for log of sigma 1 dash, E1 is the void ratio, and for log of sigma 2 dash, E2 is the void ratio. And difference in void ratio is denoted as delta E, and difference in the effective stress is delta sigma dash. Compression of a soil as a function of time at the given stress increment is expressed as compression delta H or dial gauge reading R on y-axis versus time on the x-axis. Both void ratio and pressure are plotted here on arithmetic scale, and using this curve we will be obtaining the values of coefficient of compressibility and coefficient of volume compressibility. We will now derive the equation to find out coefficient of volume compressibility. In this figure, we can see the soil mass which is fully saturated. This represents volume of solids, which is taken as equal to volume, that is volume of solids is equal to 1, and this is what is water. So volume of water is equal to volume of voids, which is equal to voids ratio E. Since the soil is fully saturated, volume of air is equal to 0. Hence, VA equal to 0, as theory of consolidation is applicable only for fully saturated soil. We know that voids ratio E is equal to VV, that is volume of voids, divided by volume of solids. We will consider unit volume of soil solids. So Vs can be written as equal to 1. And void ratio E is equal to volume of voids, that is VV. And initial volume of the soil is written as V1 equal to volume of air plus volume of voids plus volume of solids. Volume of air equal to 0. So V1 will be equal to 1 plus E1, that is initial voids ratio. But change in volume divided by initial volume is equal to change in voids ratio divided by initial voids ratio, that is 1 plus E1. We will assume constant loaded area A. So delta V divided by V1, that is change in volume, is nothing but V1 minus V2 divided by initial volume, that is V1. Vf is the final volume of the soil after a given stress increment, that is delta sigma dash. Change in volume to initial volume can be written as V1 minus V2. V1 is initial volume and V2 is final volume, divided by initial volume V1. And initial volume V1 can be written as area into height of specimen, which is the initial height, minus final volume, that is area, into final height of specimen, that is H2, divided by A into H1. When A gets cancelled out, we get equation as H1 minus H2 divided by H1. So delta V divided by V1 can be written as change in height of the soil specimen divided by initial height. So it is delta H divided by H1. We will combine both of the equations. So we get delta V divided by V1 equal to delta H divided by H1, which is equal to change in voids ratio divided by 1 plus E1. The definition for coefficient of volume compressibility says that it is a ratio of change in volume divided by initial volume to the change in effective stress. So change in volume is delta V, initial volume is V1, and change in effective stress is delta sigma dash. We have already got the equation for delta V divided by V1 as delta E divided by 1 plus E1. So that is what is substituted over here, and delta sigma dash as it is. And delta E divided by 1 plus E1 can be written as delta H divided by H1, and again delta sigma dash as it is. So coefficient of volume compressibility MV is equal to change in height of the specimen to the original height divided by change in effective stress.